Hello, physics students. We're going to talk about writing net torque statements and using those statements as a tool to solve some problems. And the problems that we're going to get into solving are called static equilibrium problems. And there are two criteria for static equilibrium problems. We'll get to those. So for right now, all we're going to worry about, for this slide, all we're going to worry about is just identifying all the torques acting on this object and what the net torque is. Okay? And so, what we have to do is, let's assume that there's this gray disk here. It has a radius r. It's fixed about an axis that goes through its center. It's a wheel type of thing, disk. And three forces, F1, F2, and F3, act on this object. They act at the locations shown, which is important, and they point in the directions shown, which is important. So let's write a net torque statement. All right, the net torque statement, or at least let's add all the torques acting on this object. Now, the question is, I suppose, a question is, which of the forces produce torques and which ones don't? All right, and as you might be able to recognize, I'm going to help you a little bit. I'm going to draw vectors r for each of these forces. Here is a vector I'll call r1, corresponding to force 1. Here is a vector r2. And here is a vector r3. By definition, remember, vector r points from the axis of rotation to the point of action of the force. All right, so what we are saying is when a force vector starts there, it means that's where the force is being applied. When F3 starts there, it means that's where F3 is being applied, similar with F1. Okay, so this tells us, perhaps right off the bat, this should tell us off the bat that the torque created by F3 is 0. And the reason that is because F3 contains no component that's perpendicular to vector R3. All right, remember, our general statement for any torque is that torque can be expressed as R times F perpendicular or R perpendicular times F. And so, if there is no component of a force that's perpendicular to its respective vector R, that force produces no torque. So F3 produces no torque. All right, F2 and F1 do produce torques because, well, F2 is perpendicular to its vector R. F1 has a component of itself, okay, that's perpendicular to its vector R. So each of those forces does produce a torque. And I'll also say this. Notice how if F2 were applied here, that would tend to make this disk rotate that way. F1 being applied where it's applied would tend to make the disk rotate that way. And those are opposite rotational directions. And so my net torque statement is going to start like this. I'm going to define, I think that the real standard definition is that counterclockwise is the positive angular direction. All right, it doesn't matter which one you choose, but if we choose that as our positive direction, I'm going to say there's a torque created by F1 and there's a torque created by F2. And those are in opposite directions, so I have to subtract those torques to get the net torque. Okay? Now, the torque created by F1 is R to F1 times F1 perp. And the torque created by 2 is R to F2 times F2 perp. Well, we should draw the component here of F1 that is perpendicular to its vector R, and there it is. All right, and well, if we say, how about we say that here's an angle theta 1 here, right? Well then R1, that angle here is the same as this angle here. So F1 perp is opposite that angle. F1 perp is F1 sine theta. Okay? Now, R1 is capital R. It's the distance from the center to the rim, and that's the radius of this actual disk. So there's big R times F1 perp. And then we subtract the torque created by F2. Well, let's see. R2 is big R over 2, and times the whole darn thing. Okay? So I really recommend people that have a tough time with net torque statements want to skip that part. They want to jump right to the putting in numbers or putting in R's and F's, and they will, because they forget to write a torque statement, actually identifying torques and adding and subtracting, what they'll in a lot of cases do is forget to involve the R's and only write the F's or something like that. So that'll come with practice, but I really recommend that judicious maybe approach of saying, okay, there's a torque created by this, there's a torque created by that, and I either add or subtract. So that this process of starting with the fundamental and then building from there, I think is a good one. All right, we could, if we feel like it, algebraically say that this is, we could factor out an R, right? And then that would be here F sine theta, and here we'd be left with that. All right. So that's the net torque, whatever number that is. All right, that number depends on what R is and what F1 and F2 are and what that angle is, but the number doesn't matter. That's how you do it. Okay. Moral of the story here, I guess, is make sure you're paying attention to direction. All right, and what I mean by that is like counterclockwise versus clockwise. Okay. Okay. Now, this isn't much of a problem because this answer would give us, we'd get an amount of torque. All right. When these become a little more interesting is when we can apply that idea to, well, how about an object in equilibrium? All right. And here we're looking, so there's like, imagine we got this green rod that's like held up by a support type of thing, or maybe it's like a axle that goes through it like that, but we're looking, this is an eyeball, we're looking from the top, all right, top view, okay? So that means that there is a gravitational force acting on this rod that is right there, but it points in a direction into the screen. So, it points like this, but since we're looking from with our eyeballs, eyelashes, eyebrows, looking from the nose, lips, you get it? Chin, oh boy. We don't see MG pointing away from us. We don't draw it on this diagram. Thanks for the art lesson there. Good, good. So here's an object. It's applied plank to a plank. We get a force F at one end, and we want to put this object in equilibrium. All right, in equilibrium. Well, equilibrium means two things for us. Equilibrium means, one, from our old days, the sum of all the forces acting on this object is 0. New and improved, number 2, it means that the sum of all torques on an object must be 0. This means that A translational is 0. An object won't accelerate along a path. This means that alpha equals 0. Or this thing will not accelerate rotationally. Okay? So, we are going to say, we're going to use a net torque approach to solve for this force at the other end that's applied here that puts this object in equilibrium. Most of you right off the bat, lots of you I should say right off the bat, have an intuition of how big that force is, but we'll prove it. All right, so we're going to start with a net torque statement, and that statement looks like this. There is a torque created by F. Now, F would tend to make this object rotate that way about this axis. We don't want it to rotate that way, so what we need is a force that would tend to make the object rotate that way. And so there's a force, let's call it A, that looks like that. All right? And so what we need is the torque from F minus the torque from A equals 0. Or the torque from F and the torque from A are the same thing. They have the same magnitude. Now the torque from F is R to F times F, and the torque from A is R to A times A. And we said that this distance here is L over 4, which means that the rest of this distance is 3L over 4. 1/4 3/4 makes up the full L. So R to F is L over 4. R to A is 3L over 4. And notice that these L over 4s can be divided out of each term, and you get that A is 1/3 of F. Sure. When we apply a force 3 times farther away, we need 1/3 the force in order to create the same amount of torque. Okay? Now, look at this. Notice. We've got a force downward, another force downward, and downward really, doesn't mean toward the floor, but it means whatever direction that is. But this thing's in equilibrium, right? So the only way it can be in equilibrium is if there's a force exerted by the pivot on the plank that looks like that. Because if there wasn't, this thing would accelerate translationally. There would be a net force, not even net torque, net force that way. This whole plank would accelerate toward the bottom of the page. Well, the plank doesn't accelerate toward the bottom of the page because there must be a force exerted on the plank by the pivot. And now we can write a straightforward net force statement where F plus A minus, let's call this the pivot force, minus P equals 0. Notice F plus A, because F and A both point that way. P points that way, so I'm subtracting. So that says that P is F plus A, or P is F plus F over 3. Oh boy, oh boy. Yeah? So that says that P is 4F over 3. All right? Any good question that involves, any good question in a torque sort of context, especially an equilibrium one, will involve the fact that you have to do both of these things. And it will always start by doing that. And second, you can almost always do that. All right, and the reason we can't start with net force is because there was no way in the beginning that we knew how big this pivot force was. And the nice thing is, if we say here is our axis of rotation, even if we know that pivot force is there, since we don't know what the pivot force is, if we say, well, here's the axis around which I'm analyzing torques, P produces no torque. So that's a big time skill, is being able to, a good question like these will involve two unknowns. And when you decide, because you will get experience deciding, to put the axis of rotation at the point of action of one of your unknown forces, well, it removes that force from any torque statement. All right, notice we got nothing about torque created by P here, because the torque created by P around that axis is nothing. Okay, let's look at another one. here's a rod. Okay, it's got that mass. It's balanced on a fulcrum by an unknown force at its left end. Find the normal force. Find F. I bet. Let's see. We I might, if I were you, do part B first, but I'll show you that we can do part A first. All right. And here's a big deal. Any and every good problem is going to start with a free body diagram. All right, and a good one. So here's one. On this plank, there is a force mg. The plank's weight acts at its center of mass. There's a force F at its left end, and that's got to be downward. And I know that because mg would make this thing want to rotate that way about this axis. So F is going to make it want to rotate that way. Those are opposite rotational directions. F's got to be downward. Of course, if you want to hold up a plank like this, you're going to push down on its end. Well, look, those are two downward forces, but this thing's in equilibrium, so there must be a force normal, I'll write on plank by fulcrum. So there's our free body diagram. All right, and we got two unknowns. Here's one of them. What's F? And two, what's that normal force? Well, two unknowns means we can't write a net force statement. I mean, it is true, right, from a net force perspective. That's a F. It's true that F plus mg equals n. But there are two unknowns in that. It's unsolvable. The net torque approach is solvable because we can choose where our axis of rotation is. Now, this thing will actually rotate about this fulcrum point. All right? But I just want to show you this. Just because the object actually rotates about that axis doesn't mean we have to do a net torque analysis around there. All right? And in particular, question A says, what's the normal force? So what I'm going to do is choose to keep the normal force in my net torque analysis. And the way I do that is by saying, I'm going to measure torques generated about the end of the rod. And you say, but the thing doesn't rotate about the end of the rod. Yeah, okay, it doesn't. You're right, but it doesn't matter. All right, I can now say that if I look at torques generated around the end, there's an R to the normal force. There is an R to mg. And notice, right, around this axis, we still get this rotational direction from mg. And around my left end axis, n creates the tendency for this thing to rotate this way, and those are opposite rotational directions. So now we can say there's a torque produced by n, there's a torque produced by mg. Those are in opposite rotational directions. And here's the big thing. Net torque equals 0. Without saying it explicitly, up here we did say that net force equals 0. That's why those two downward forces equal the upward force. All right, so this says that the torque produced by the normal force equals the torque produced by mg, or R to the normal times the normal equals R to mg times mg. Or the normal force is R to mg times mg divided by R to n. The normal force is R to mg. This is a 5-meter long plank. From the end, R to mg is to the center of mass. That's 2.5 meters. mg itself is 12 kilograms times g, 120 newtons. R to n, well, notice, it's 3.5 meters from n to the right end. So from the left end to n, that's 1.5 meters. And that's 5/3, 140, 200, right? Sure. Probably. Call that 200 newtons. Now, it's fairly straightforward to find F. We can say that F is N minus mg, or F is 200 newtons minus 120 newtons. F is 80 newtons. What say you? I say great. Notice, we will approach by first running a net torque analysis to find one of the unknown forces. 2, run a relatively simpler net force analysis to find the other unknown. Oh, my hint here in the text of the question, hint for all kinds of questions like these, assume the weight force acts at center of mass. Because in effect it does. Okay, one more. Irregular shapes. Here's a neat one. I want to show you this guy. Let's see. Here's a semicircular. They're 1 meter in diameter. Weight W. 2 wires. What's the tension in each? Here, this is a good one. A free body diagram looks like this. There is a tension L that acts there. It does. And here's a tension T right that acts there. And the center of mass of this semicircle is there-ish. And so mg looks like that. All right. Now, we don't know either of these tension forces, so the right approach is to say, I'll put my axis of rotation at one of the points of action of those forces, and therefore the torque created by, in this case, TL is nothing. And there are two torques, one created by mg, one created by T right, and those two torques must be equal and opposite for the net torque about the chosen axis to be 0. All right. What's pretty neat is, watch this. Here's R to mg. R to T right is easier. It looks like that. R to, I'll just write it as capital R. The problem with R to mg is there's an angle there, and if you don't know where that, even if you do know where that center of mass location technically is, that angle's not simple. But what we can do, a great thing about analyzing torques is we can, if you remember, extend the line of action of mg, and then this is R mg perp. So there's a torque created by T right. There's a torque created by mg in in opposite directions. So I can say minus torque from mg is 0, or we get that these two torques are equal and opposite. And this is R to R times T R. I don't have to worry about perp anything because they are perpendicular. R to R and T R are perpendicular. Now, this I'm going to write as R to mg perp times mg. And then we don't have to worry about any of this angle stuff. It doesn't matter. What matters is, here's the perpendicular part. It's just like saying mg produces the same amount of torque as if it acted right there. So R to R is 0.75 meters. I'm going to write that as much as, if I call this the diameter D, I'm going to say this is 3/4 of D. And R to mg is, to make it easier, I'll call it 2/4 of D. And then your D over 4s go. And this says that T right is 2/3 of mg. Right, number one is our, let's write a net torque analysis. Number two, now there are three forces, two of which we know. So number two is let's now write a net force equals 0, and we get TL plus T right equals mg. TL is, excuse me, sorry, minus T right. TL is, well, mg minus 2/3 of mg, that's 1/3 of mg. Each of those two ropes have to add to the tension force. I'm sorry, add to the weight force. So one of them's 2/3 of the weight, the other one's the other third. Fair enough? Okay. These get a little, this will get trickier because there's angles involved. So we'll get there soon. Okay, this is a different sort of question because it talks about these forces exerted by the beam, and this is a trickier one. All right, so in another video we'll look at more challenging net torque or equilibrium problems, I guess you'd say. All right, but for cases where everything we can turn into a R that's perpendicular to a force, these are great examples of pretty standard static equilibrium problems. Okay? Okay.